Right. So yeah, I also want to talk about observables. So let's talk about observables and the algebraic index theorem. Okay. So the algebraic index theorem is sort of an approach using, say, deformation quantization or some ideas coming from quantization to discuss index theory and also sort of to discuss index theory in the non-commutative geometry. So what's the theorem? So this is attributed to Nest and Segan. And then I'd like to sort of suggest and outline an alternative proof that's joint with my co-author, Owen Gwilliam. And our sort of proof follows very much in the spirit of what Kevin talked about this morning. OK, so what's one way to state the theorem? So X is a manifold. OK, then I want to say that the cyclic homology of something that I build out of the differential operators on X, that I can identify this with another complex that I build out of the forms on the cotangent bundle. And I have these this formal parameter h bar and this parameter u.
And that equivalence is a quasi-isomorphism?
Yeah, so I'll just state it as a quasi-isomorphism. And
h on both sides, but only u on one side. So maybe that's fine.
Yeah. I mean, this is cyclic homology, so. And then the differential starts to look really funky. So let me just write it and then explain the pieces. OK. And if you're keeping score at home, this guy is a degree 2 parameter. And you might say, like, well, that seems kind of funny. But the notation here is to suggest that this is not sort of the standard de Rham complex, but I sort of put the k forms in degree minus k. And I sort of view the de Rham differential as going backwards. But now UD actually has degree +1. So it's a little funky. But this is the Poisson homology differential. So this is like the lead derivative with respect to the Poisson bivector coming from the symplectic form here. And this is the interesting part. This is roughly an analog of the a roof class that you would expect to see in sort of like an index theorem. Since I have this parameter u, this thing gets sort of adjusted a little bit. But maybe I spell that out in detail.
UD has degree +1.
Yeah, UD has degree +1.
Because D has degree -1.
Right. Yep. OK.
So that formula in the parentheses is the differential of that complex, the total differential or something?
Yeah, this is, yeah. OK, so.
Just a little bar after the a hat and a comma. That's just the argument.
Yeah, exactly.
Huh?
Yeah, exactly. So this, basically, as we'll see later, hopefully, this is, you sort of think of this as coming out of a BV construction. And this actually is sort of the BV bracket. Everything has an interpretation in terms of these field theories. And that's naturally where those guys live. And so that bracket has a nice interpretation. So a remark is in order. Sort of like why you might call this an index theorem.
What's L pi?
Yeah. So this is the Poisson homology. So it's the lead derivative with respect to pi.
Since you mentioned field theory, what kind of field theory do you have in mind?
Yeah, actually, it's going to be exactly one of the perturbative field theories that Kevin discussed this morning.
Which
Yeah, it's going to be like it's going to be a 1D Chern Simons theory, where the gauge group is not. I mean, it's actually sort of it's an L infinity algebra. So.
You could say it's quantum mechanics.
Or it's also topological quantum mechanics if you. So it'll be a rewriting of sort of quantum mechanics in the style of Chern Simons. So.
Can you discuss the grading of the term h bar L prime?
Yeah. Well. So I mean, this if you can use the Cartan formula for this, and so I.
Okay, but I mean, I usually think of it as having degree 0, but and then h would have degree +1. So it doesn't. But what do you think h has? H is usually degree 0, right?
Mm-hmm.
2.
Yeah, normally I don't. So it depends. So this h.
Interior multiplication with pi should have degree 2.
Right. Yeah.
And the d has degree -1.
So I think it should be. Yeah. So if I mean, this should have degree 1, so this can have degree 0.
L has degree 1.
Yeah. So this should make sense of a
L
different.
has degree 1.
Write down the bracket. Write down.
I mean. Right. So this is, I mean, and then the funny thing is that the complex is in a funny sort of, is organized in a funny shift. So this should have degree 2, this has degree -1, so the commutator has degree +1.
Oh, pi is a 2 vector.
Yeah.
Ah, okay, fine. Sorry.
Sorry. Okay. Okay, so let me, I don't want to say too much about sort of why this is called an index theorem beyond to say that you know that sort of this is related to Hochschild homology, and Hochschild homology is sort of the universal trace. I mean, any trace will factor through Hochschild homology. And further, in their formulation of the theorem, Nest and Segan actually go on to show that you can deduce from this theorem the Atiyah-Singer index theorem. So of course, that's sort of, so me and Owen are sort of on that path, but there's still some work to be done. It's maybe not so clear exactly how to link up with what Nest and Segan do. Okay. Right. So what's the sketch of the proof? Okay. Well, it's going to be
on the left-hand side a little bit. I mean,
sure.
algebra with differential operators, or
Yeah. So this is actually the Riesz algebra. So differential operators is a filtered object. So anytime I have a filtered object, I can form the Riesz algebra. So
is
yeah. So it's things of the form h to the I, say fi x. So I just sort of weight the pieces that live in the ith filtered piece by h to the I. Okay, and then multiplication sort of is the obvious thing. And the Riesz algebra is a nice construction because it sort of makes explicit how to think of a filtered object as a deformation of its associated graded. So so this is this Riesz algebra. And then I just take I mean, maybe it'd be more clear if I wrote Hochschild homology here, but somehow I'm thinking of, secretly I have a circle action going on. I want to take circle invariance at some point. So is that okay? Okay. So what's the idea? Well, the idea is to construct a field theory on R So it's going to be a one-dimensional field theory for any smooth manifold X.
Can you set H equal to, like, is this only like a formalized form? It doesn't work. Can you make it like non-formal? You set H equal to a number, like, a small number.
I mean, so for me, it's just a formal parameter. But I mean, if you're familiar with sort of like, so this, I mean, this makes sense. This sort of makes sense, right? When H is invertible or when H is non-invertible, and that's sort of how you realize this deformation picture.
Right, but I'm saying when H is invertible, if I understand correctly, you get differential operators. Is that not?
That's correct.
And then the question is whether you can make that isomorphism convergent, but like if you said H equal to some.
What H? Well, I mean.
Like does that isomorphism converge?
Well, I mean, when it goes to 0, it's the associated graded, so that's
right. But first, yeah, like if you, like, I guess if you put differential operator, then you remove the H. You said H bar equals something like, some small value.
Yeah, I mean, it's possible, but it's sort of not how you might be able to get away with this, but that's not how I'm thinking of the problem. So, Kevin, do you have something that you wanted to? Okay. Okay, so right, so I want to construct this one-dimensional field theory, and then the right-hand side will be the global observables. And this Reese algebra will be the local quantum observables. And then the left-hand side is just equal to the factorization homology of the local quantum observables. Okay. So, okay, so that's the talk. So now I'll sort of discuss the various pieces in here. Before I get to constructing the field theory, let me discuss sort of observables and the structure that they possess. Excuse me. So probably some of you are familiar with this. But yeah, I'd like to discuss factorization algebras. So factorization algebras are something sort of like pre-Cauchy's, and then they have this with some extra properties. So let M be any space. A factorization algebra on M is an assignment F of U of a chain complex for any open set in M. Okay. So I should note here that, yeah, my factorization algebra is taking values in chain complexes. You could sort of choose a different target category, but I'm just interested in chain complexes. And so we need we satisfy some conditions. So if U is contained in V, then I get a map F of U to F of V. And this has to be compatible. Right, so if I have U and V and W, But then I have the obvious sort of diagram. So this should commute. Okay. Right, so let's suppose that I have now a collection of open subsets that are pairwise disjoint.
So is this a strict object or what is it? I mean, is it up to prefer homotopy or is it strict?
I'll take strict.
F isn't strict.
Yeah. You can relax things suitably if you would prefer, but I'll take strict. OK, so for a collection of pairwise disjoint open subsets, I get a map excuse me, from the tensor product of what I assign to each of the individual open subsets to what I assign, the chain complex I assign to the large ambient open subset. And right, there's sort of a locality condition. So maybe I phrase this as f is determined by its values on small balls. So you can spell this out. You can sort of spell this out in more detail, but it's a technical thing that just says sort of provided I know what f assigns to a small enough a collection of sort of generating open subsets, I know what it does to any open subset. Okay. And one way that you might think about this, and I'll see this in a second, is that you should think of this factorization algebra as sort of assigning observables in some sense. So it's sort of the measurement you can take, say in your in a field theory, and you should think of this condition too as being something like a star product or something like this. So it provided that two observables are not taking place sort of in the same neighborhood, I can actually sort of define a product on them. But let me delay that conversation. And let me give an example. OK, so now I'm going to define factorization algebra on R. And it's going to be coming from an associative algebra. OK, and so and it's not going to be very interesting. It's going to assign my associative algebra to any open connected subset of R. Okay, and you can see that, yeah, okay, this sort of, I mean, it satisfies this condition, obviously. And, well, how do I get the, how do I see the second, how do I see this multiplication map? Well, I just use the, so this is U1, U2, V. Well, then I just use the algebra multiplication. Right, so keep this by A. So if I have the inclusion of two smaller open subsets into a bigger subset, well, I can, what can I do? Well, I can just use the multiplication on the algebra A. Okay.
Would we, I mean, if you just take any manifold takes the differential operator supported on an open subset, would this be an example?
Can you repeat the question?
Yeah, sorry. So the question is, given any manifold, to an open subset, assign the differential operators supported on that.
I don't know what about 3. The others? And of course, the map is 0.
But what's the map? What's 2?
Yeah, I don't know what
is
I don't know about.
You multiply.
0?
You multiply, but
I mean, I guess that's like an honest co-sheaf, right? And so you just sort of could try to define the 0 multiplication. And yeah, so I haven't thought through this locality axiom, but certainly it seems like you have a chance of making that go.
But it is not this.
No. It's not that, right? So we'll see that that's actually that's going to be a factorization algebra that lives on R. And so it's going to assign, and it's going to be one of this form where I assign associative algebra to any open subset. What's that associative algebra? Well, it's this Rees algebra. Right. So this might seem like sort of a silly example, but in fact, there's a theorem that sort of, at least in the homotopical context, goes back to Jacob, or you can find this the strict statement is in Owen's thesis. So it says that there is an equivalence of categories. So here I have associative algebras. And here I have, say, factorization algebras, let's say on R, which are translation invariant. So if my factorization algebra is sort of translation invariant, then I can always realize it as this sort of form. And that'll be sort of manifest when I construct the field theory, because it'll have sort of this translation invariance, which means, OK, the observables are of a particular form, and they just need to identify that algebra. OK?
Do you also need to include dilation invariance on the right-hand side?
Yeah. So the inclusion of a small ball into another is a strict isomorphism. And so you can lose the strictly and work on Rn, and well, then you replace associative algebras by En algebras. So sort of factorization algebras are a formalism that sort of, in particular, subsumes En algebras. OK. So now it's sort of a fact that factorization algebras satisfy descent for group actions. And so what do I mean? I mean that if I have a G equivariant factorization algebra on a space M, well then I get a factorization algebra on M mod G. And one particular example of this is, so suppose that we identify S1 with R mod Z, and suppose that I have a sort of factorization algebra on R. So in particular, this FA that I constructed here from an associative algebra is a Z equivariant factorization algebra on R. And so it descends to 1 on S1. And I can sort of compute its global section. So I can say, well, what does it associate to all of S1? So I might also call this taking factorization homology. And you can identify this with a tensor the Hochschild complex. OK?
Does your group has to be discrete?
Yeah, I think that
Okay.
it needs to be discrete here. OK, so if you're sort of trying to sketch the proof in your head, you might try to sort of you might say like, OK, well the left-hand side of that theorem looks a lot like sort of the Hochschild complex, and so I bet I'm taking factorization homology over the circle of this factorization algebra that I construct from an associative algebra. What's the associative algebra? Well, it's already on the board also. So that's what we'll do here. OK. So I sort of hinted at this earlier, but these things are sort of show up naturally when you consider observables in quantum field theory. OK. So what's the data of a classical field theory? So Kevin gave a nice definition this morning, but let me sort of organize the data in a slightly different way. So it might look sort of more familiar. Or possibly less familiar. OK? So what Kevin called L, I call E. So script E. So this would be sections of some vector bundle. OK? I have a degree 1 differential, an interaction term, and this invariant pairing. So this is a degree +1 differential. So this is typically a Z-graded vector bundle. This is a local functional on E. So what do I mean by local functional? Well, I mean that only really depends on the value of a section and the jets of that section. It doesn't something that's not local would be to say like, OK, we'll take the value of a field over here, take the value of a field over here, and multiply them. So that's not something that I'm interested in allowing.
So is that like the action then?
Yeah, it's part of the action. Right? So this is the quadratic part of the action, and this is the interacting part of the action. Right? So if I let phi denote a section here, then the action S of phi is equal to phi. And I have q plus I. Phi, and I take this pairing. So in this right, so in this example that sort of Kevin alluded to this morning, so Chern Simons theory. So 3D Chern Simons theory. So we had that our fields were something like forms on R3 manifold with values in a Lie algebra, and this gets shifted. Q was just equal to the de Rham differential. And what should I be? Well, I just equals sort of the, it's sort of given by the Lie bracket here. So the action, so this is, well, at least up to some constants. So let me neglect some constants here. D alpha plus, or 1/2 plus 6 alpha. Okay. So this sort of should remind you of the typical sort of Chern Simons action. Okay.
So you have alpha. Can you read that for me? That cubic term. Alpha.
Yeah. So it's alpha paired with alpha bracket alpha.
Oh, bracket. Okay.
Yeah.
Alpha. Is there a D in there?
So there's a.
Why don't you just write it over here? I can't really read it.
Also, your D's and alphas look very similar.
Well, that's not. I can't see very well.
That's true. Yeah. So I'll write it over here, but first. So I would use a capital D, but there's something else that's coming for capital D. So so what's the action? Well, I pair alpha with D alpha, and I add to that. So I'm neglecting constants here. Right. Okay. And this. So this invariant pairing is quite simple. I assume that M is oriented compact, and that the Lie algebra comes equipped with a pairing. It's pair the Lie algebra elements, wedge the forms, and integrate over the manifold. Okay. Okay. So let me say sort of what a quantization of a classical field theory is. So what does this consist of? So this is a collection of interaction terms. So these are functions excuse me. So initially I just sort of had one interaction term, and there was no L involved. So now I have this family of interaction terms, and it depends on this parameter L. Okay, and moreover, it can have an expansion. It's a power series that also involves this formal parameter h bar. Okay, and this needs to satisfy some conditions. So let me just write them down and then sort of explain verbally. Yeah, so that's so it's like they're like formal power series in the field. Okay, so the first one goes by the name of the RGE, the QME, locality, and let me write down the quantization condition. Okay, so so let's forget these first three. So the last condition essentially says, okay, yeah, so if I pass to sort of the classical limit of the theory, so my length scale is going to 0, I want to recover my classical interaction term modulo some h bar sort of terms I may have added along the way. locality is a technical condition, so let's ignore this one. RGE stands for the renormalization group equation. So it says that these action functionals I of L, well, they're not just sort of arbitrary functions of L. They depend in a nice way. They sort of, there's actually they're a one parameter family. They satisfy a differential equation. Okay, and the quantum master equation is sort of an algebraic. It's sort of an algebraic gadget that sort of asks questions about how this renormalization process is compatible with sort of some natural operators we have, like the BV Laplacian and the BV bracket. Okay, so these are the conditions that we want a quantization to satisfy. Okay, and I'd be happy to talk at more length afterwards about any of these guys. So let me forego that far side of the board.
Are two different forms of the same thing?
No. Yeah, so in fact, the typical sort of, if you wanted to sort of build such a quantization, you can try to do a naive thing where you just sort of enforce the renormalization group equation, and then you need to check that it satisfies the quantum master equation.
But it's a consequence. If you do it right, it's a consequence. If you don't do it right, it's not a consequence. Or you want it to be.
I mean, so for instance, you might be familiar with, say, like Kevin's work on the Witten genus. So he does, well, anyway, so he wants to quantize the theory. And so he sort of does like a naive quantization, which satisfies the condition 1. But there's a non-trivial obstruction to satisfying condition 2, which is like the second Chern character. So, I mean, I would argue he seemed to do 1 correctly, and 2 wasn't automatic. It actually it's an interesting sort of consequence. Okay. So. Okay, so I told you all this factorization algebra business, but first let me just write down a chain complex, which comes from the global observables. Okay, so we have the global observables. Okay, so first we have the classical ones, and we have the quantum ones. Okay, so what's the chain complex here? Well, so it's this completed symmetric completed symmetric algebra in the field, and it has a differential, which is sort of the transpose of the differential Q, plus this operation determined by the interaction term. Okay, and what are the quantum observables? Well, so there's some dependence sort of on this length scale. So that counts for this part. So let me simplify things a little bit. So I'm going to say the quantum observables at scale L. So this L and that L are the same L. So as a vector space, it's pretty similar, except I've adjoined this formal parameter h bar. So this operator is called the BV Laplacian.
The bracket, does it inherit an L dependence as well?
Yeah. Okay, so I don't really want to say too much about sort of the BV structures here. Hopefully you're either familiar with them or willing to take my word that they're interesting.
The observables are the Chern complex or the cohomology?
Well, so I would like to think of them as the chain complex. Think of them as the chain complex. Okay, and so a remark is in order here. So this chain complex actually has additional data. It comes equipped with a Poisson bracket. So this guy has a Poisson bracket. Excuse me. Of degree +1. And so I might call this structure. So it's a chain complex equipped with a Poisson bracket, a P0 algebra. Okay, and this also has sort of a Poisson bracket. I mean, this has a bracket, but the bracket and the differential are not actually, they're not quite compatible. So
Differential, that entire differential?
the Q. Yeah. So this has a structure that's called a BD algebra. So I mean, I guess you'd like to call it a BV algebra, but sort of the degree of one of the operators is slightly different. So Kevin and Owen coined the term BD algebra. And the reason why I make this remark is that one way to think of quantization is to say, I start with a P0 algebra. So forget all the stuff I did on the far right boards. I start with a P0 algebra, and I want you to give me a BD algebra that is in a natural way of quantization. So that's another way that you can sort of formulate what this quantization procedure is doing. Okay.
But that's a differential, but the Q is not a derivation of that curly bracket. Is that the incompatibility you said?
Yeah. Right. So the failure of actually the failure of Q to be a derivation of so Q and the BB Laplacian sort of they fail to. This fails to be a derivation of this, and exactly the failure is the bracket.
You say that in different words. Q and delta don't commute, you mean?
That's
Anti-commute or whatever. The total thing is square zero, right?
sorry. Right. So this has a right. So this has an, I'm sorry. I should have said it differently. So this has an algebra structure,
Yeah.
and the failure of this to be the failure of Q to be
Derivation.
a derivation is measured by the bracket.
Okay.
Yeah. Sorry. So I think that's
The total thing is square zero.
that's right. That's a consequence of the QME.
And delta is a derivation of bracket, and Q is also a derivation of bracket? Or
Yes.
a derivation of bracket?
Yes.
All
Yes.
three?
Yes.
Okay.
Okay. Okay. So I thought maybe I would do a simple example to give you some feel for sort of why this makes any sense. Okay, so let me.
So before Q is a derivation of that algebra, right? On the classical side.
Mm-hmm. Yeah, I mean, Q is just coming from sort of this chain complex of fields. And then you pass the dual while I just take the transpose of it. Yeah.
Is an H missing in front of the curly bracket?
I don't think. I don't think I want an h there.
In particular, when h goes to 0, right, you want to recover
Yeah.
that, so there's no h there.
So sorry if there's an extra h floating around earlier, possibly. Is there? It's okay. Okay. So oh right. So the other remark here is that we can also define so local observables, and they form a factorization algebra.
The problem is someone says no h, then it's confusing that this Emil Laplace has anything to do with this. Because there's this h and the other thing has no h.
Yeah, but the whole thing is an algebra over.
Yeah, but I mean, somehow then this thing is, some of these things have to be 0 and 7. I mean, we can do later actually.
I mean, so the question is about sort of like why the h bar is only floating around here in front of the BV Laplacian.
Well, no, he's drawing implications from the form of the formula. Like when you square that, you get lots of different terms. A lot of things have to vanish.
Sure.
So he's wondering if you really mean that.
I do mean that, yeah.
Okay.
But I think the term that you need to vanish should you can sort of argue via this quantum master equation. So I didn't tell you what it is, but it involves these three guys.
Are there an incompatibility of Q and this Laplace L is the bracket? But I mean then.
So I misspoke. So I didn't mean to say that. So they're yeah. So anyway, maybe I go on and we can sort this out afterwards. Is that okay? So this is sort of a subtle thing because in order to say like what the support of an observable is sort of a difficult, or at least sort of a somewhat technical point. So I don't want to spell this out, but the point is that global observables form chain complexes, local observables form factorization algebras. Okay, and so I wanted to give you an example. So let's take a Riemannian manifold. Okay, and I want my fields. So this complex E. Well, this is dimension n. So I'm going to have smooth functions, and well, I sort of trivialized the density line bundle. So I think of these as being sort of I really think of this as I could replace this by top forms. Okay. And so the pairing here is hopefully pretty clear. It's just multiply and integrate. Okay, and so suppose that we have typical elements. So here I have a phi, and here I have a psi. Okay, so I want to discuss sort of some classical observables. And here's the cohomological degree. Okay, so suppose that I give you a pair of these guys. Well, one thing I could do is I could say, OK, well, evaluate this function at a point. Okay, and this has cohomological degree 0. So hopefully it's clear. My convention is that this lives in degree 0, this lives in degree 1. I think that's fairly clear. So if I instead evaluate psi at a point, this has cohomological degree -1. And or I could do sort of more interesting combinations. So we could do, say, phi of x, phi of y. x. Do something like this. Okay, so these are just sort of examples of classical observables. So of course there's many more, but these are sort of the typical examples. And what is the differential? Well, the differential applied to one of my psi guys, so applied to the observable that just says evaluate psi at x, is given by Plossian of phi x, and it annihilates the phi's. Okay, so then you can compute the cohomology of the global observables, or in this case you can also do the local ones. Let me do the local ones. So here I have the local. I have the quantum observable supported on an open set U, and
what's Q in this example?
yeah, so Q in this example is the Laplacian.
But you're applying Q to psi, and psi is over on the right.
So this is the Q on so on the field level it's the Laplacian. Then on the observable levels that's sort of that's power series in the dual space.
So you haven't said this sentence, I think, that observable is a function on fields.
Yes.
Is that what we're supposed to be thinking?
Yes.
Okay.
Yeah. So if you think of fields as sort of being something like physical states of your system or something like this, an observable is a measurement you can make. Okay. So you call up your friend in the physics department and say like, okay, build me a detector so I can measure that.
So on the right-hand side, when you're writing on now, the psi's, are the elements in E or in E dual?
So this assignment is an element in E dual.
But when you write on the right-hand side here, when you write Q of psi, is that Q the differential in the original complex or in the dual complex?
I mean in the dual complex. But
So the symbol psi on the right-hand side means an element in the dual space.
yeah, I'm saying what the differential on observables is. Sorry, it's a little complicated because of how I chose to write things as typical elements as phi's and psi's, and then the observables also as phi's and psi's.
I think maybe the slight confusion was that, so it's just the order E. For the second gadget, that second assignment,
Yep.
you apply Q to that, and that's what you wrote in the first line, right?
Yeah, so the point is that this line is applying the differential on observables to this observable. And so I expect to get a new observable. What's that new observable? Well, it's saying evaluate the Laplacian of a guy psi at x. Okay, so the classical observables are just sort of generated by these Q's and P's, which you might think of as sort of being the delta functions and the delta function for the first derivative at a point. And the quantum observables are a bit more interesting. So, well, I still have my Q's and P's. Now I have this formal parameter h bar, and there's a relation here. So the relation is qi pi minus pi qi minus h bar. So I cut out by this ideal for all I. So this should look something like the Weyl algebra plus this parameter h bar, which is sort of what you might expect to get for this free field theory.
It's kind of hard to believe the first line because positions or Q's and P's are first derivatives, like evaluating first derivatives, but you put a Laplacian. You put a Laplacian up there.
Yeah.
It's hard for me to believe that. This is a second derivative, and these are first derivatives. Simplify.
Right. I mean
Some integration by parts going
So
on.
yeah, so you know that things that involve the second or higher derivatives, actually are going to be co-boundaries. So that's the point. So there's no way to get a first derivative by using the Laplacian, but I can sort of construct all the second derivatives and higher.
Right. But, so what do P's and Q's mean? They don't mean the usual thing?
This sort of means, so these correspond to sort of evaluating at a point, right? So you have the different, and these correspond to evaluating the first derivative at a point. So I don't have second derivatives and higher because they'll be co-boundaries.
Ah. Oh, I see. Okay.
So I think you were saying the right.
I see. Okay.
Yeah. So I think you were saying the right thing. It just didn't quite.
Okay. I'm not computing cohomology correctly.
Yeah.
Okay. I see. Okay. Fine.
Okay. What's U? So U is just an open. So U is an open subset of M. So it's probably easiest just to do the computation just for where M is equal to, say, R or something like this. Okay, and then have things have compact support. But okay, so what's sort of the main theorem to sort of such that this algebraic index theorem I stated will be sort of a corollary, or some more work, I guess. So for X, a smooth manifold, there exists a one-dimensional Chern Simons theory so I can say more about this in a second, such that the local observables, so this is a translation invariant theory, so the local observables would just be given by an associative algebra, and they're given by this Riesz algebra differential operators, and such that the global observables, so now this is just a chain complex, is this funky this ginormous complex. H bar. Okay, great.
What does the first line say?
So
Quantum observables, first line. Quantum observables, what was that?
So-
Is that quantum observables?
yeah,
Applied to U or the differential forms?
the Riesz algebra of differential operators. So this is a one-dimensional theory. So think about living over R. Okay, and it's going to be translation invariant. So we know from our discussion that it's just going to essentially correspond to an associative algebra. So I have to tell you the associative algebra. This is the associative algebra. Okay. Okay, so that's sort of the statement of the theorem. So this is with Owen. So I don't have so much time left, but let me just say a word about sort of what the theory is. So the theory is so it's sort of studying the moduli of maps from the circle into X, but just in a neighborhood of constant maps. Okay. So if you want to link up to sort of what Kevin discussed this morning, this is one way to sort of write down this theory. And why did I call it sort of a 1D Chern Simons theory? Well, in order to sort of make this, to convert this into sort of this vector bundle language, I sort of do this funny thing where I try to encode the smooth geometry of X into the structure of like a sheaf of L-infinity algebras. And that sort of, I can use that L-infinity algebra to write down something that looks very much like three-dimensional Chern Simons theory. And so they sort of have this similar flavor. So after telling you sort of what the theory is, I think that this is a good place to stop. So.
Any questions?
So when you say global observables, you mean on an R, on the real line, is that right? Like global sections of this quotient.
Yeah. So you're right. So when I write down here, I'm thinking of this as sort of being on S1, actually.
So that's my question. I'm a little confused about that. This looks like S1 invariant, say, sections on S1, but our field theory was on R.
Yeah. So first we construct the field theory sort of on R, but it'll be a translation invariant field theory.
Do we expect a dependence on the size of our circle?
So the identification of the chain complex won't depend on the size of the circle. So some of the explicit computations actually do. You do need to sort of fix the size of the circle, but in the end, it sort of gets washed out. So it really is a topological theory. It won't depend on the size of the circle. Yeah.
So I mean, just for the logic, I mean, does this give an independent proof of this, or do you use this result to deduce? I mean, that you get this global thing from the local thing?
No. So right. So the logic is that by proving this theorem, you can deduce the statement of the index of the algebraic index theorem.
So you get an independent calculation of the global observables, and then you.
Right. Exactly. The point is that there's two sort of ways to compute the global observables. There's sort of like this a priori way that I told you just how to write down the chain complex. But then I also have this local to global principle where I compute the local observables, and I can use factorization homology to compute the global observables. And I see that, yeah, OK, when I do the two different ways of computing the global observables, I get the left-hand side and the right-hand side of the statement of the theorem.
He's saying this theorem is naturally in the picture of these quantum field theories. So it really gives a new perspective on the proof and a new proof.
And moreover, it sort of, this story is not specific to sort of one dimension. I mean, this sort of, you have this phenomenon where you can, if I write down interesting theory, say on elliptic curve or something like this, you might hope to sort of make some sense out of the local to global computation of observables in that setting as well. Yeah, Ewan?
Maybe this follows from David's question. You told us in your previous story to take Hawkshew homology as to give like the structure of the circle. Maybe explain why are you taking circle invariance? Like why cyclic homology? So if I were naive, like I would have followed what your previous procedure and just applied HH.
Yeah.
I presumably would not have got this, but would that have been interesting?
So Ewan asked, like, OK, well, why do I have circle invariant stuff floating around? And that's sort of a subtle question. So some of the nature of the constructions of this right-hand side are such that if you didn't take circle invariance, you'd end up with nothing on the right-hand side. So this is supposed to be a characteristic class of the smooth manifold. And if I just wanted it to live in sort of some complex I built from differential forms, but I didn't include the circle action, then it would vanish when I passed a cohomology. So my interesting class should be interesting. So that's why I need to have the circle invariance. So this is a bit of a subtle thing. So I'd be more than happy to chat with you afterwards. But
we're still.
I mean, maybe just one difficult question. I mean, some of the original theorem of Ness theorem and so on. I mean, in the definition of the cyclic homology, I mean, you use topological cyclic homology in the sense that you, I mean, if you take, say, write down the standard complex, something like this, then you complete the tensor products. And somehow it seems that you have a completely algebraic or argument here where you don't complete. So somehow, so how can you match? I mean, the cyclic homology, I mean, in Hochschulpost Rosenberg and this kind of theory, usually it's, I mean, you work with Richter spaces to complete tensor products and so on. And here it seems that you just do algebra.
Could I ask it in a more positive American way, sort of? I mean, you're sort of saying, this has to be wrong, you know. No, you have a principle, you said, of computing from local to global. There's some idea. I don't think you said that idea during your talk.
Oh.
What is that idea?
Oh, so the idea is that the point is about sort of this local to global construction, and Uli sort of has a question about how to get the cyclic homology out without sort of completing the appropriate algebras, right? So, but the point is that if I know what the local observables are, then I can just, so that's defined, that's sort of like a Cauchy thing, so it's defined for any open set on my manifold. Well, I could take the whole, I could look at global sections.
Yes.
And so the statement is that global sections of local observables agree with, are really global observables.
I mean, they're quasi-isomorphic.
Yeah, yeah.
So that's the theorem. That's a theorem. It's not a definition. It's a theorem, right?
Yeah, I mean, I guess it's just sort of. Yeah. So it's not it's not obvious, right? There's some that this complex that I told you to write down is exactly what you want to get out at the end of the day. But.
I mean, in this axiom 3 that you didn't say, the local implies that the factorization algebra is determined by the tiny balls.
Uh-huh.
I mean, where is it happening? I mean, okay. We both had the same question, different form. Where is it happening, this quasi-isomorphism? He says, following from a general principle. Where is that general principle?
Well, so the overarching general principle is like I said, like that. Yeah, the proposition is that there's two ways to compute the global observables. Or to sort of, when I have a QFT, this perturbative QFT, there's two ways to compute the global observables.
What are the 2 ways?
The 2 ways are I can compute the local observables, that's a factorization algebra, and I can compute the global sections of that factorization algebra.
That's one way.
That's one way.
So that the global sections is more or less the right-hand side, or that has to be computed to be the right-hand side?
Yeah, so this is computed. This is sort of an a priori this is sort of an a priori construction of the global observables. So the statement of the theorem proceeds by identifying the local observables, and then knowing that the global observables over the circle are the Hochschild homology. And then if I insist on sort of having this circle invariance, then I pass to the cyclic homology. Okay. Whereas this just follows from a direct computation of how I defined the global quantum observables. Okay. So hopefully that at least hints at a break in the skies, maybe.
Yeah, but I mean, still, I mean, if you just take this definition of Hochschild homology using, say, the S1 going to S1, I mean, this computes the algebraic Hochschild homology.
Yeah.
Without any completion, without any.
Yeah, no.
I mean, so how can you compare?
So I think he's saying that the Sigon theorem must be expressed in a technically different language about the definition of Hochschild's homology.
I think it's not the algebraic Hochschild homology. It's some completion.
I'm not sure. I thought that it.
I mean, aren't you already completing when you write out these expressions in head? I mean, you tick and complete things, right? So completion is happening in the process here.
But I think that the question was sort of more the difference about sort of some topological Hochschild versus Hochschild, and I don't think that.
I mean, yeah.
I don't think that I have topological Hochschild homology. topology going on. I just have the algebra. This is a purely algebraic sort of construct.
I mean, somehow, but if you, for instance, if you put h equal to 0, then you get Hochschul-Kosten-Rosenberg out of it. But this is, I mean, the Hochschul-Kosten-Rosenberg is.
I mean, if you have a smooth, but I mean, you have smooth algebras. I mean, like, do you?
I mean, they define the Hochschul-Komplex different.
Okay, it's
Let's do it later.
All right. One more.
Well, actually, you have to use multi-differential operators or something to find complex.
Was that your suggestion or a question?
I maybe try to answer that question.
Uh-huh.
Okay, well, on this positive note.